just to set the stage for what we did last time and what we are going to do this time. So in a sense, at the center of what we discussed is decoherence. Last time, we have rebuilt the foundations of decoherence by discussing how selected states come about and by deriving Born's rule. So Born's rule was the subject last time, and what I would say quantum jumps or einselection where the foundations we laid under decoherence. This time, we are going in the opposite direction. Decoherence is about what the environment does to the system. What we shall talk mostly about today is what does system do to the environment, and this goes under the slogan of quantum Darwinism. Okay, so this was last lecture, but we always start here. Yesterday or last week we started here, went down. Today I'm going to remind you of what we did, but then this is going to be the focus. As last time, I welcome questions. I will probably stop a couple of times, but if there is something urgent, I do not mind stopping and discussing it. So we start by talking about decoherence and einselection as a reminder, because it is a foundation of quantum Darwinism. By the way, my two most recent and still ongoing collaborations are with Jess Rydell and Michael Zwolak, and I shall be using extensively results that they have obtained. We are done with quantum jumps and quantum origins of probability, but I shall offer a brief reminder of the bottom of the foundations. To remind you of the general theme is we are going beyond decoherence. So in a sense, there was this fortress, impregnable fortress of how to interpret quantum mechanics. Decoherence was the first break in the wall. Now we got in and we can explore it, both the cellar and the rooms above. These two papers, especially the most recent one, the one in Physics Today last year, cover a lot of the material that I shall discuss today. So our other way to think about what's going about to happen is to try to reduce the number of axioms that appear in textbooks of quantum theory. This is a good textbook, Dirac. I've outlined the axioms, or I've extracted the axioms in the order in which pure mathematics appears on the top. So systems, states of the system are represented by vectors in Hilbert space. Evolutions are unitary. This is pure math. If we have vectors, if we have systems which are composed of more than one piece, then their states live in a tensor product of constituent Hilbert spaces. That's important. This allows for decoherence. These top 3 are only mathematics. You can do every calculation you ever wanted if you have these 3 ingredients, such as Hamiltonians, initial states, etc. It's clear that only mathematics doesn't yet have tie to physics. So in order to establish tie to physics, Dirac adds several axioms. I like the one that immediately follows, number 3. Immediate repetition of a measurement yields the same outcome. It's known under the name repeatability. I call it predictability. It's the same thing. It basically tells you that if you know the state, you can confirm it is there. Outcomes, axioms or postulates that are not equally liked and that are controversial for good reason are so-called collapse postulate, which has 2 pieces. One of them says outcomes are restricted to orthonormal states, eigenstates of the measured observable. Another way of saying it is observables are Hermitian, as well as just one outcome is seen each time. These come out of the blue. Apparatus is described by quantum mechanics, so it should be possible to infer out of the mathematics of quantum theory and some very rudimentary connection with experiments, outcomes which are high level and look arbitrary. The last outcome, the last axiom, the last postulate is about probability of finding an outcome, and it simply says it's a square of the amplitude. It's Born's rule. So the overarching question, and especially the question we shall focus on today, is why do we perceive our quantum world? Because, you know, whenever we test, these rules seem to hold. Why do we perceive our quantum world as classical? The ones in the yellow rectangle are the ones we are allowed to use to understand the answer to this question. So that's our program for today. What we did last time is we derived in a very minimal way why outcomes of measurements are restricted to classical. So the key was repeatability. We insisted that a state of a system that is measured by the apparatus, so state is U here, apparatus starts in a state A0, that state is measured, so it makes a change in a state of the apparatus, but the state of the system remains the same. If we insist that the state of the system remains the same, repeatability would be respected, and other apparatus would be able to confirm it's still in a state U. Same for the state V. And we've derived just from very rudimentary assumptions orthogonality. Let me remind you how it went. The key point is to recognize that the evolution, according to quantum theory, must be unitary. If the evolution is unitary, scalar product of these 2 states on the left-hand side and scalar product of these 2 states on the right-hand side must be the same. So this equation must hold. Now, this is an equation which is almost trying to suggest a simplification. But if you were to simplify by dividing by a common factor, you would conclude the measurement could not have happened because this quantity must be 1. And if this quantity is 1, AU is equal to AV. So there is no difference between the 2 states of the apparatus. It can have no imprint of the environment whatsoever. Now, we've realized this simplifying business was too rash. There is one case where you cannot divide both sides by the scalar product, and this is precisely the case we are after, when scalar product is equal to 0, division is illegal, and this is a proof that repeatable measurements are possible only in the case when the states which are measured repeatably by an apparatus, possible outcomes, are orthogonal. We've not used probabilities. The only values of scalar product we appealed to were 0 or 1, so this is completely independent of the red axioms on the previous transparency. The other, so predictability implies restriction to orthogonal states. In a sense, this gives us on a platter quantum jumps, right? It says that if you want to have a set of states which can be repeatably found out or make repeated imprints on anything, including the environment, which will be key in the rest of the lecture, then these states ought to be orthogonal. It can be extended, discussed. It proves that the states must belong to a Hermitian operator, so it proves 4a one of the postulates from Dirac. So in other words, predictability implies restriction to orthogonal states. Moreover, it prevents you from finding out a pre-existing state. Quantum apparatus that allows you for repeatability is not going to let you find out a state that was there before. You can only find out an answer to the question that is posed by the apparatus, and these answers are orthogonal. So this suggests collapse. This suggests a set collection of possible outcomes. We have also used very basic ideas, symmetry, to derive probabilities in quantum setting. So how it went? Well, we started with a very simple entangled state, an entangled state where a coefficient differ only by phase. Now, this entangled state has the property that you can change these phases acting by either on the system or on the environment. This is sort of obviously you have an operator which rotates this phase in some direction by another factor delta. You can apply an operator unrotating it to the environment. A similar operation, slightly more complicated, but with the same property of symmetry, can be applied in the case when the coefficients differ only by the phase to the, let me actually go back, to swapping of these states. So I can take state Sk and put it to where a state Sl used to be. This operation will do it. This is like shuffling cards. I can compensate by the phase in the meantime, and then I can undo that operation by acting on the environment. So this is simple. This is like shuffling cards. In other words, I take this initial state, I shuffle hearts with spades, I end up with a completely different entangled states of the two systems. So S lives in one place, E lives in the other place, but I can restore the global state by shuffling states of the system E. Because of that, I know that the probabilities when the coefficients are equal must be equal. And the reason for that is straightforward. I have shuffled things by working on the system S, but then, so the probabilities must have been swapped, but then I have undone that shuffling without touching system S, so locally, probabilities must be the same because the global state got restored. Probabilities are both the same and exchanged. That happens only when they are equal. This can be generalized, and this is a basis for Born's rule. I will not bore you with algebra, but the key thing is that you can always reduce a situation where the coefficients are not equal to a situations where they are equal. And the way to do it is by fine-graining, and the bottom line is you obtain Born's rule. Moreover, you obtain it without the need to assume additivity, which is a plus in a theory where an overarching additivity principle is a superposition principle. So that was summary of the foundations. We now have looked at the foundations. We now will look again at decoherence in a slightly different way than last time to prepare ourselves to discuss quantum Darwinism. So the plan of the whole enterprise was why measurement outcomes are limited to orthogonal subset of possible states. We have that. Why does Born's rule yield probabilities? We have that. Now we can use usual tools of quantum theory, reduced density matrices, etc., which rely on Born's rule to get the rest, to discuss decoherence and to discuss transfers of information, which will be crucial. So our goal is now how objective classical reality, states that we can find out, arises from fragile quantum states which can be perturbed by measurements. Reminder of decoherence: the system is entangled, the system is immersed in the environment. The interaction Hamiltonian between the two means that the state of the system becomes entangled with the state of the environment. When that interaction Hamiltonian is fixed, usually it happens so that the same sets of states end up on the diagonal of the reduced density matrix. In particular, in simple cases, these are simply the states which commute with that interaction Hamiltonian. So preferred observable is a constant of motion under the Hamiltonian of interaction. In other words, these conditions select preferred states, states which are immune to the interaction with the environment. This process was known and is known as environment-induced superselection. It limits the set of states which can persist and therefore exist in a normal sense to just the pointer states. Now, last time we have had reservations about using it as a foundational starting point because of the trace operation, which is involved in obtaining reduced density matrix. Trace operation is in effect averaging. Averaging involves Born's rule. We wanted to derive Born's rule. We now have it, so this is legal. So we have derived Born's rule. We can proceed as decoherence was practiced for last 30 plus years, because we are already done with understanding that indeed Born's rule gives you probabilities. Preferred states. So decoherence gets rid, in the language of reduced density matrix, of the terms which are off-diagonal in the preferred basis. That density matrix which is left after decoherence happens, the coefficient on the diagonal can be interpreted as probabilities. And if you have many different states and you don't know which ones are going to be preferred, which ones are going to survive interaction with the environment, you can apply what we call predictability sieve. Pointer states entangle least with the environment. So if you have a list of all the possible states to begin with, and look at how impure they become at the very end, so calculate purity, trace rho square, states which are left purest are the candidates for your pointer states. So you can think of having a peak in purity in the Hilbert space. You can do it the other way around. Purity is easy to calculate. Quantity, which has in some sense more or better justification, is entropy. So you could calculate entropy here, and then the states which would have least entropy would be near the peak, would be the candidates for classical states. Now, entropy enters into a discussion, and I would like to dwell on it a little bit because it will play an important role. In particular, the quantities that I shall focus on is mutual information, because this will be useful. And I will talk here, so entropy is going to be computed here most of the time using von Neumann's formula, which is there. And I will discuss here a situation where you first have a system which interacts with the apparatus. The state becomes entangled. Then I will go on to discuss decoherence. And this will be a sort of preparation for the discussion of what happens to information when it flows into the environment. So when you have, first of all, if there is no correlation between the system and the apparatus before they have interacted, their density matrix would be given by a product of the density matrix of the system and the density matrix of the apparatus. It is two independent probability distributions. In this case, what you don't know about both is equal to the sum of what you do not know about either. So joint entropy is equal to the sum of the two entropies. Now, mutual information is a way of telling how much two systems know about each other. It is given by the sum of the entropy of one system, entropy of the other system, and the entropy of both of them jointly. Think of two books. If it's a copy of the same book, what you do not know about the content of one is exactly the same as what you do not know about the content of the other. But if you have two of them together, you still don't know the same amount. It doesn't double because it's the same book. So in this case, mutual information will be entropy of one plus entropy of the same one minus entropy, the same entropy, because in this case, probabilities are not independent. In fact, joint information is just equal to either of them. So if they are independent, this is 0, but following a measurement, this will not be the case. And here I'm talking about a first stage of the measurement. I start with a system in a superposition of up and down. It interacts with the apparatus in a state A0. This is an interaction Hamiltonian. Boldface is Hamiltonian. Italic is entropy. And now the two are correlated. When the two become correlated, there is a single entangled state of the two. I can calculate the reduced density matrix of the system by taking a trace over the apparatus, or I can calculate the reduced density matrix of the apparatus by taking trace of the system. The coefficients are the same, so when I calculate entropies, they will come out to be the same for both the system and the apparatus. And indeed, that's what must be happening. However, the combined system is in a pure state. The whole thing is still pure. If the whole thing is still pure, then von Neumann entropy is 0. The two systems are so perfectly correlated that we know the state of the whole, even though we do not know about the state of the other. In this case, the mutual information is therefore Hs plus Ha, which is the same as 2Hs, minus 0. Twice the entropy of a single system. With books, or with any other classical system, this would have been impossible. In fact, with books or with any other classical system, the largest value of the mutual information is the information content of the lesser of the two parties. So, for two books, this is bounded by a book. If you have a book which has 2 volumes, but you lost 1 volume, then it's going to be bounded by the volume which you still have. Now, let us add to this mix the environment. And here I shall let the environment interact with the apparatus. This is a normal setup in the laboratory. Quantum system can be tiny and very well isolated. Apparatus is plugged into the wall, there is air, photons bounce off it, etc. What happens then? Environment is going to now interact with the apparatus, interaction Hamiltonian, and it will measure, in effect, its state. I shall assume that that measurement by the environment is good, in the sense that the states E plus and E minus of the environment are orthogonal. So I now have the following state, entangled state of 3 systems. Now I can calculate again density matrix of system and environment. Before, this density matrix corresponded to a pure state. Now it corresponds to a mixed state because the environment has found out the state of the apparatus. So now that density matrix looks like this. The eigenstates, the probabilities are still the same, but now here are correlated states of the system and the apparatus. So here we have a situation, in a sense, of 2 classical books. When you find out the state of the spin, you find out the state of the apparatus and vice versa. But beforehand, you don't know which of these states is going to materialize. There is a classical correlation here, but there is also ignorance. So after decoherence, partial entropies are all equal. Entropy of the system is still going to be given by what it was given before. Entropy of the apparatus is still going to be given by what it was given before, because the eigenvalues, probabilities do not change, but the entropy of both of them is also given by the same. So now the mutual entropy between the two has decreased to what it was allowed classically. It is saturating the classical bound which before we have violated. Of course, we can now say, wait a second. There is the mutual information between the system and the apparatus, but I could include environment in the mix. The whole state is pure, and I would be again in the same problem or in the same situation where mutual entropy would be above the classical bound. And we shall have to think about it again. But the point is, environment removes just the right amount of information to retain classical correlation, but to get rid of quantumness. If there are any questions at this point, I'd be happy to entertain them. Okay. If there are none, let's get back to what we want to do. Let's see. Decoherence domain selection, we've discussed how much it does. Thesis, quantum theory can explain emergence of the classical. Decoherence restricts stable states to preferred pointer states. We can select them using predictability sieve and selection, etc., etc., etc. We have now seen it from the point of view of entropy. We have now seen that mutual information goes down to what it's allowed classically when decoherence happens. What else is there to do? I mean, aren't we done? We know what states are preferred. Well, we would be, except we are dealing with quantum mechanics. Measurements of observers redefine states, right? This is what one of the axioms of quantum theory says. You come in and you measure and you present the system with a multiple choice test. The system cannot give you an answer which is not one of the legal answers on the multiple choice test. So even if the state of the system is different, you don't know what it is. You will just find out the answer to your question. So why don't we, observers, redefine the state of the system each time we look? That is the question for the second half of the talk. And we're going to answer it. And the answer is basically fairly simple. The answer is that this theoretical model of how we perceive the world, where we interact directly with the object we want to find out about, is wrong. We never do that. So, marche pas. Typical observers never interact directly with the system. What we do instead, systems and observers are based in the same environment. In this case, there is a sun behind. In this case, there are lights here which shine on the system of interest. I am, at this point, hopefully the system of your interest. Since I am the system of interest, two things happen. One of them, air, but especially photons, bounce off me and spread the information about me all over the place. And we have direct evidence that there are many copies of that information, because each of you intercept with just a little bit of your of the square footage of your eye, tiny fraction of the photons, and you find out everything you need to know. So we need to understand what sort of information can get multiplied in multiple copies and delivered to many observers. So the environment carries these records, which it obtained while decohering, all over the place. They can be carried, they can be accessed by observers often extremely rapidly. Many redundant copies assure observers can agree. That's quantum correlations. That's mutual information. And this is the source of objective reality in a quantum universe. So in some sense, it's sort of the medium through which we receive our information, which restricts the sort of messages, which does not allow us to perturb the system because we never measure it. We live off the information we intercept from the environment that has measured it. Environment will amplify only certain information, and we are now about to analyze in more detail how that happens. My collaborators over the years, Mike Zvolag and Jess Rydell, most recently and still ongoing discussions on this subject. So this is quantum Darwinism. Darwinism, by the way, two elements of it. One of them, survival of the fittest, but this was already in decoherence. This is in selection. survival of the fittest states which can survive. Second, multiplication of the information about them, proliferation, right? And this is, by the way, where the states which can survive being copied matter. In order to have many copies, you have to have an original which can withstand copying. So this is where pointer states reappear. Mutual information. We already went through it. We are going just simply to change notation. So what we want to do is we want to find out what fragments of the environment know about the system. So we change the optics a little bit. Before, it didn't matter that the environment consisted of parts. There was just one big monolithic environment. What you worried about is what this environment did to the state of the system. Now our question goes in the other direction. We have a system and we want to understand how does it imprint its state or information about its state on the environment. And we want to recognize now that the environment consists of many parts, many photons, for example. And how do we get an information about the system of interest, not directly by measuring it, but by intercepting pieces of the environment, collections of photons, right? So key to us is mutual information between the system, which is the same as the system and the measurement problem was before, but now the notation changes. Fragment F plays the role of the apparatus. Most of the time, in fact, all of the time, from our point of view, most of the environment gets away. So the fact that it gets away is, in a sense, system is still as a system, apparatus is now fragment of the environment, and the rest of the environment assures that this pair is decohered. So quantum mutual information, system entropy plus fragment of the environment entropy minus entropy of the two. It measures information in correlation between the system and the fragment. There's no reference to observables or measurements because these are just reduced density matrices. And quantum mutual information is bounded by this more generous bound that is saturated when you are dealing with pure entangled state. And what we shall want to understand is how much mutual information does a fragment carry or supply, because that's how we get our information about things. And redundancy, how many disjoint fragments supply almost all information that we are interested in. Right? So these are the sorts of questions which will be the center of our attention. So in other words, and this is just repeating what I just said, mutual information is key tool for quantum Darwinism. When mutual information, like in the case of the apparatus, is equal to the entropy of the system, the apparatus can fully reveal the state of the system. And in quantum Darwinism, fragment F of the environment will play the role of the apparatus. Its correlation with the system will often be effectively classical, as the rest of the environment will decohere the pair of interest. So let us proceed. Let me start with an extremely simple example. I have my system, and I have my environment, and it's a modest one. It just has two subsystems, E1 and E2. I'm going to let the system interact with the apparatus. The interaction is so-called controlled knot, where the state of either piece of the environment is completely enslaved to be the same as the state of the system in this basis. So at the end, I get this state, right? The whole state is pure. The fragment could be either E1 or E2. Now we have a symmetry we won't have for much longer. So whether we trace over this or this fragment, we are going to get a density matrix which has always this form. The first one represents the state of the system, the second, the state of the fragment of the environment, the subsystem we are interested in. After decoherence, they are classically correlated. And here is a somewhat lengthy proof that they are classically correlated, but you know it already from the previous discussion of measurements, so I'm going to go on. Now, there is, if they were uncorrelated, mutual information would be 0. Now, quantum mutual information can exceed classical information. Again, the state of the whole is still a pure state. So, joint entropy in case F is identically equal to the whole E is 0 because the whole state is pure. So in this case, mutual information will jump up. Any questions at this point? Please. There is really no direct connection except that the states which I've written down would violate Bell's inequalities, right? So I think the best I can say is violation of Bell's inequalities and violation of the inequalities between information go hand in hand. Okay, so let's plot partial information, mutual information, between the system and a fragment of the environment. So here I have my very simple example, just from before. Here is a classical information. In this case, it's 1 bit, right? Because that's how much we don't know about the system. And this state is already pre-entangled, right? So initially, if we haven't measured any piece of the environment, we are here. We don't know anything. But now we intercept a single fragment of the environment. Well, we don't have that many fragments here. So that mutual information is immediately 1. It reveals the state of the system. However, if we manage and measure in the right way to intercept the whole thing, the mutual information would jump up to the quantum level, F equal E. In this case, the whole environment is treated as a fragment. So if we manage to capture all the photons, we would be able to recover quantum coherence because having all of that mutual information at the quantum level means we are violating Bell's inequalities, etc. Okay, let's enlarge our environment a little bit. So now I have 3 subsystems in the environment. Again, you jump up from not knowing anything to the level 1. So let's grab a little bit more of it. Well, yeah, we have grabbed more of the environment, but we haven't learned anything new. And the reason for that is that there is this perfect correlation between the state of the system and the state of the environment. You already found out everything that was to be known about the system by finding out the first bit of the environment. However, if we intercept all of them, it still jumps up to the top. Okay, let's keep on going. It's the rest of the lecture. 1, we jump up, we know everything. 2, we still know as much as we knew was 1. 3, not much better, but if you exhaust everything and if the state of the whole thing was pure, you recover full quantum coherence. You kind of don't need to know what happens with 5, 6, 7, etc. to guess what happens, right? So the curve is going to be very boring in this case. You jump up from not knowing anything with the first bit, in this case, to knowing everything. This is a plateau which continues until you run into the n-1, the very, very last one, and then it jumps up to. So the lesson in this extremely idealized example is you find out classical information from small fractions of the environment. But in order to recover quantum coherence, you would need to intercept and measure in the right way everything. For reasons which I think are clear by now, we call this classical plateau. The question we want to analyze is how many copies of this information is in the environment. And in this case, because we've used such an idealized example, where every bit of the environment knew everything that was to be known about the system, the redundancy, R, is simply equal to the number of subsystems in the environment. So in principle, this many observers could find out independently about the state of the system, and they would agree. Of course, this is an idealized version of so-called branching states. They follow from decoherence, right? I mean, the process which happened here was the same process as measurement and the same process as decoherence, transfer of information that favored a certain set of states. In real life, copies are going to be imperfect. And also, photon won't carry the information about all of me. I'm not a two-state system. So one has to be a bit more realistic about it. And in real life, the curve I drew very schematically on the previous one becomes curved. What you can prove, however, in the case where the whole is pure, is that this curve is anti-symmetric around the point 0.5 and entropy recoverable about the system from the fragment, from half of the environment. So it has to look like this, right? It's anti-symmetric around this point, roughly speaking. So now let's do our trick again, but let's ask a question which is more realistic. I do not want to have all the information about the system. You don't want to know my quantum state. You want to know something about it. So I'm going to be satisfied with, with less than all of the information about the system. Delta is my tolerance for errors. It's an information deficit I am willing to accept. Now, suppose there are many observers, many photons bouncing off the system, each of them is looking, etc. Suppose here's my observer, he looks from far, or his eyes are small, or he doesn't get that many photons, he just gets one single photon. That single photon gets him only up here on this curve. Two photons, well, two photons are better. Now he intercepts more, so he knows better, but he's still not happy. Three photons, yes. Okay, he got to where he wanted to be. In this case, redundancy is going to be essentially the number of bits, number of pieces in the environment divided by the number of pieces you need to have in a fragment which makes you, typical fragment which makes you happy with the information you've obtained. By the way, you know, if you are an astronomer, you are not working here. You are building telescopes because you are somewhere here on the bottom and you have just very little information and you need to gather big fragments to get what you want. If you are in the lab, you are closer to here because you can possibly get to good information about a quantum state of the system. So notice still, at the end, because there is this anti-symmetry in the case if the whole thing is pure, there is potential for recovering for whole coherence. But you can imagine it's going to be exceedingly difficult to capture all the photons and measure them in the right way. So another way of thinking about redundancy is you find out what fraction of all the environment gets you over the top of where you want to be in terms of how much you want to know about the system, and redundancy is simply an inverse of the fraction of the environment that supplies you with the necessary information, and the necessary information is defined in part by how much you're willing to accept or how much you're willing to forgo. By the way, this shape of curve, which we have just seen, is not a typical shape of mutual information for the Hilbert space of a system which is composed of n pieces of the environment and one small system. Right? So if I were to ask a question, which is a very well-defined question, I have this huge Hilbert space. I have a pure state in it, and I pick a state in it in random, and I start in this state measuring bigger and bigger and bigger and bigger pieces of the whole thing. How much information about a system with which it's correlated or the whole thing I would gain by measuring, the curve you would actually obtain and the curve that can be derived analytically is this green one. You find out almost nothing until you are halfway through the whole Hilbert space, and then all of a sudden you find out everything. It's sort of surprising, but it's simply true. And you can derive it, and Don Page did it in a context of something that has to do with black holes many years ago, and he guessed the answer, some Japanese proved the answer. So it's true. So the states which are coming out from decoherence are really the states which are very atypical. They give us, or they possess branches, each of which inherits states, information from the systems they've measured, from the pointer states of the systems they've measured. And the states which are able to survive being copied into the environment over and over and over again are necessary for these sorts of curves to arise. Am I running out of time, or how? 5 minutes, 10 minutes? Okay. So this was all extremely, well, fairly abstract, simple models, etc. Let's look at something which is, well, let's summarize. Think about questions. I'm going to ask for questions in 2 more minutes. And let's look at something which is realistic. So almost all quantum states are non-redundant, right? The green line. They do not give you many copies of the information. You basically have to measure half, and then you know everything, but measuring half of any environment is an impossible task. Redundant states we infer from observations are exceptional. How do we explain that? Well, I mean, we need to put in special initial state, entropy. In equilibrium, you would have this green sort of curves at best. Special dynamics, decoherence, which favors certain set of states. One would like to understand how these states come about and how they decay in a realistic model. So the last few minutes is a realistic model. Collisional decoherence. Sun or light bulbs, shining photons. This is the environment at a system. My system is going to be idealized, but not ridiculously idealized. I will consider one micro, well, the sizes don't matter at this point. I will put a sphere of dielectric because it's easy to do calculation if it's a perfect dielectric, of a certain size in a superposition. So it's a Schrödinger cat state. It exists in two positions at the same time, right? And I will try to find out how many copies of the information about where it actually is are inscribed in the environment. Amazingly enough, because when you calculate mutual information, you are scared of the fact that you have to take logarithms of density matrices, and that means diagonalization and so on. Amazingly enough, this problem, without too much idealization, can be solved exactly. The answer can be written in terms of decoherence factor, which is how much the off-diagonal terms of the density matrix of this Schrödinger cat gets suppressed. This is solved in models we consider, which is photons. So we really do a scattering calculation, right? There's a field theory, plane waves coming from the left, hitting this thing and scattering all over the place, right? This gives you a decoherence time. So decoherence factor is an exponent of the decoherence time, and mutual entropy turns out to be this amazingly simple after you look at the derivation formula which where the main ingredient is this gamma. By the way, you can factor in the fact that the light source could be close to a point light source like sun, or that the light source shines from all over the place. It turns out once the light source shines from all over the place, the environment is unable to accept any information because all of the modes are occupied. So whatever scatters already into a mode which has photons, so you can't tell from the environment what happened, where the object is. People who make pottery know that, right? So if you have a kiln in which you bake your pot after you've made it, if you make a small hole, you don't see anything because everything is black body radiation coming out of there. You have to shine with different frequency or do something, or let the kiln cool. That's the same effect. So this is captured by this factor. We are going to work with a specific value of this alpha. How many, what part of the sphere is occupied by the source? Okay, wait, I went too far. Voila. No, here. Okay. So, and to cut the story short, I mean, the calculation is, turns out it's surprising. To me, it was surprising it can be done. The bottom line is you can calculate, you have a closed form formula for redundancy, and you have a formula which was given by the sum on the previous transparency for the mutual information curves, right? The ones I was drawing before. Here they are parameterized by how many decoherence times I've allowed to elapse. So initially, 1/10 of a decoherence time, that is beginnings of the information that are leaking. After one decoherence time, or whatever this is because it's 10 power, you end up with a curve which begins to look like it is developing a classical plateau. After 20, you have a very sharp curve. After a couple hundred, you basically go up immediately, you stay flat, and you would need to grab last few photons in 10 to the 20-something in order to recover quantum coherence. So from this, you can also calculate how does redundancy depend on various factors. The nice surprise is it's very weakly dependent on what you ask for in terms of accuracy. It's logarithmically dependent, so it's a very gentle dependence. good notion of the record. It's linear in time. Photons scatter all the time, so as you keep on waiting, there is more and more records that are being produced. And the redundancy rate is proportional to and capped by the decoherence rate. So production of redundancy cannot be bigger than decoherence because of this problem with modes being already occupied by other photons which don't accept any more information, but this is true. So production of records necessarily decoheres. That's another obvious thing. If you have records in the environment that are lost somewhere, that means you have decoherence. Just to give you some numbers. So again, dielectric sphere, a speck of dust, right? So tiny piece of dust, 1 micron in size. Just Schrödinger cat is not very big. Last lecture I had 1 centimeter, 1 gram, and so on. This is much smaller. 1 micron dielectric sphere, 1 micron separation between the two components. The radiation comes from the sun. So this is a temperature of the radiation that comes from the sun. You make 100 million copies of the information of where this speck is in just 1 nanosecond. So you are on one of these curves with mutual information which go immediately up, stay flat forever until last few photons. Summary. We never directly measure systems of interest. Instead, we intercept fragments of the environment that know about what the system is. So we, in a sense, use the environment as a communication channel or as a witness which knows about the state of the system. Preferred observable is the only one which can be inscribed in many copies in the environment, and this is justified by this pre-decoherence argument. Survival implies orthogonality. Observers can only intercept fragments of the environment, so we can't find ever anything else except what has been inscribed in multiple copies. Many observers can access information of interest indirectly without infecting them with measurements, and they will agree on what they see. And this is why decoherence is relevant to what we see. So it's not that, decoherence delivers copies, that decoherence makes only certain states stable. It's more than that. It makes copies of the states which it allows to be stable. And not all environments are good at decohering and serving as a channel. In fact, decoherence due to air is more effective than decoherence by photons. And yet, we don't really use air much as a channel. The reason for that is air molecules talk to each other, they scatter from each other, they mess up the information they have acquired. Observers can't disentangle that. Photons only scatter from the objects of interest, but they do not scatter from each other. So they deliver that information reasonably pristine. Revisiting our initial goals of the whole thing, textbook quantum mechanics, we've relied on the yellow part of this transparency, simple quantum axioms plus repeatability, and we've derived definitely for A. Whether we have explained for B or not, I think will remain a matter of taste. Evolutions were clearly unitary, so all the possibilities are there. On the other hand, we are restricted to finding out only about the possibilities which are reproduced in many copies in the environment, because that's how we acquire our information. And as a summary of the whole thing, quantum states are fragile. Only the unselected pointer states survive decoherence intact. Observers intercept fragments of the environment to obtain information about systems of interest, quantum Darwinism. Only states that survive decoherence and repeated copying can be found out. Existence of preserved states can be inferred without using Born's rule, explaining why observables are Hermitian. That's the bottom part of the foundations. Born's rule can be then derived using symmetry arguments, and therefore emergence of objective reality in our quantum universe can be understood with minimal, consistent, and purely quantum postulates. The quantum credo, the yellow part of the previous transparency. Thank you.
Thank you.